Mhm.
With a
Ah,
pleasure, I introduce our next speaker, Professor Leonid Kurdachenko from Ales Gonchar Dnipro National University, who will tell us about the structure of some pre-Lie algebras.
Ну, по-перше, я хочу подякувати організаторам цієї конференції. Вони продовжують в дуже важких умовах робити це. Я нагадаю, що в середу була масована атака на Київ. Тим не менш, вони проводять ці конференції, проводять їх на дуже високому рівні. Так що треба їм подякувати за це. So I want to speak about some non-associative algebras. So some notes. Uh, First, some notice. Uh, Here we mean here a ring means the set with two binary operation, addition and multiplication, such that R is abelian group by addition, and R satisfies this usual two distributivity law. So, as usual, ring R is associative if multiplication is associative. In every ring, we can define the associator by the following rule. Associated of three elements x, y, z is product xy on z minus x on yz. So, ring R is associative if and only if associator of every three elements is zero. So, about algebra. Algebra means vector space with multiplication such that by addition and multiplication A is ring and A satisfies the following equality. Now, and left pre-Lie algebra is a vector space with two binary operation, addition and multiplication, such that by addition A is abelian group and A satisfies the following equalities. So first, this is basic. Xy on z minus x on yz is equal to yx on z minus y on xz. So, and two distributivity laws. And converse, a right pre-Lie algebra is also vector space with with addition and multiplication, such that instead of this equality, A satisfies this equality. So x y on z minus x on yz is equal to xz on y minus x on zy. So if A is a right pre-Lie algebra, we can define new operation, new multiplication by the following rule. And then A by addition and new multiplication is left pre-Lie algebra. And converse. Using the same transformation, we can go from left pre-Lie algebra to right pre-Lie algebra. So every assertion about left pre-Lie algebra has analogy in right pre-Lie algebra and converse. I prefer to work with left pre-Lie algebra. So here term pre-Lie algebra will mean left pre-Lie algebra. So an algebra A is called B symmetric or isosymmetric if A is left and right pre-Lie algebra. This algebra has been introduced by Kleinfeld, and this type of algebra were studied before the pre-Lie algebra. So if we use associator, then for left pre-Lie algebra, we have the following equality. Associator xyz is equal to associator yxz. By this reason, Weinberg called this algebra left symmetric algebra. He studied this algebra in this paper, and we can see this. It was too much ago. So, and pre-Lie algebra appear here from some question of geometry. The term pre-Lie algebra first appeared in paper or Herschel-Haber in this paper. And another term, quasi-associative algebra, appear in the paper of Cooper-Schmidt. So, and about the term, some authors wrote that the term pre-Lie algebra is not correct. For example, Fahini wrote that more exact is the term pre-associative algebra. But I use here the term pre-Lie algebra. So, clear every associative algebra is pre-Lie algebra. And I want to know the following. Every commutative pre-Lie algebra is associative. Oh, so here is the short proof of this fact. So another type of pre-Lie algebra are the Novikov algebra. An algebra A is called Novikov algebra if A is pre-Lie algebra satisfying the following condition. xy on z is equal to xz on y. So now we consider the relationship with pre-Lie algebra and Lie algebras. For any algebra, we can define the commutator xy. Commutator of element xy, and it is the product xy minus yx. And we come to the next type of algebra. An algebra A is called Lie admissible if A is a Lie algebra by addition and commutator operation. First example of Lie admissible algebra is associative algebra. It is possible to prove that an algebra A is Lie admissible if it satisfies the following equality. So it's possible to check that every pre-Lie algebra satisfies this equality. So every pre-Lie algebra is Lie admissible. And if we consider L by the operation addition and commutator operation, then we say that L is adjacent Lie algebra of A. So for pre-Lie algebra, in usual way, we can define the term subalgebra, and subalgebra generated by subset M, and the term finitely generated algebra. So, and usual way we can define the notion of left-right ideal and two-side ideal. And if we consider the factor algebra of pre-Lie algebra, then it's not hard to see that this factor algebra is also pre-Lie algebra. I want to show some properties of pre-Lie algebra. So let A pre-Lie algebra, then the sum of ideal and subalgebra is subalgebra of A. So about product, I want to show. So if A and B are subspace of L, then product A on B will denote subspace generated by products A, B, where an element A before the subspace A belong to the subspace A's, and element B belong to subspace B. So if HK are ideal of A, then product HK is a left ideal. In particular, if H is an ideal, then product H on H is left ideal. If H is an ideal of A, then product H A is an ideal of A. So, in particular, product A on A is ideal of A. So next, if H is ideal of A, then H on A plus A on H is ideal of H. If H is a left ideal, then product A H is a left ideal. And if S is subalgebra of A, then S is subalgebra and subadjacent Lie algebra. And H is ideal of A, then H is ideal of subadjacent Lie algebra. So, and now I want to speak about nilpotency, distinct notion of nilpotency and in pre-Lie algebra. So let L be the pre-Lie algebra. Put L power 1 in brackets is L, and recursively L power alpha plus 1 in brackets is product L power alpha in brackets on L. And of course, if lambda is limit, then we take the intersection of all previous term. So, and we note here that L power alpha in bracket is an ideal of L. So we say that pre-Lie algebra A, L is right nilpotent if L power n in brackets is 0 for some positive integers L. And in similar way, we put L power 1 is L, and L power alpha plus 1 is product L on L power alpha for all ordinal alpha, and for limit we can take again the intersection of all previous. So here L power alpha is only left ideal of A. We can say that Preilly algebra L is left nilpotent if L power n is 0 for some positive integers n. And the next notice, as for associative algebra, we can extend every Preilly algebra to Preilly algebra with identity. It's so. Next, define now the lower central series of L by the following rule. L, gamma 1 of L is L, gamma 2 of L is L power 2 in brackets, so this is product L on L. Gamma 3 of L is the product gamma 2 of L on L plus L on gamma 2 of L. And for all ordinal alpha, gamma alpha plus 1 of L is product gamma alpha of L on L plus L on gamma alpha of L. And as usual, for limit, we can take the intersection of all previous terms. The last term of this series is called the lower hypocenter of L. And the length of this series we will denote by this. And we will say about lower central length of L. So in usual way, we can define the notion of annihilator, left and right annihilator, and annihilator of subset. I want to say that if M is subset of A, then left annihilator is subalgebra N in subadjacently algebra. And if M is left ideal, then a left annihilator of M is ideal in subadjacently algebra, but not in general, not in L. So we define the left, right, and center of Preilly algebra. Left center is the set of all element x such that product x y is 0 for all element y of L. And right center is the set of all element x of L such that product yx is 0 for all element y of L. And the center is the intersection of left and right center. So if A is Preilly algebra, then left center and center are the ideal of L. But right center is not necessarily ideal. Starting from center, we can define the upper central series by the following rule. Zeta 1 of L is the center of L, and recursively zeta alpha plus 1 of L over zeta alpha of L is the center of factor algebra L over z alpha of L. And if lambda is limit ordinal, that we zeta lambda of L is union of all previous. The last term is called the upper hypercenter of L. And we can define the upper central series of Prelie algebra L. If L coincides with the upper hypercenter, then L is said to be hypercentral Prelie algebra. So next, let L Prelie algebra and A be the ideal of L such that B lies in A. Then the factor A over B is called central if A over B lies in the center of L over B. This means that product A L and LA lies in B, and the sum LAL plus LA lies in the B. We note that every factor of the lower and upper central series is central in L. And I want to show the following important property of the hypercenter. Let A be a left Prelie algebra if K is not zero ideal of L such that upper hypercenter of L includes K, that the intersection K with the center is not trivial. Now we consider central series of Prelie algebra. This series is called central if every factor of this series is central. So, and now we obtain the following properties of central series. Let A be a Prelie algebra and this C0, C1, and so on, Cn is finite central series of A. Then Cg lies in zeta G of L. So zeta n of L coincide with A. In particular, we obtain that the upper central series of L is at most n. And gamma G of L lies in C n minus J plus 1. So gamma n plus 1 of L is 0. And we obtain that lower central length is at most n. And as corollary, we obtain that upper central series and lower central series coincide. So Prelie algebra over field F is called nilpotent of nilpotent class n if the product of every n plus 1 element of L is 0 for any arrangement of the brackets. And n is the least positive integer with this property. So, and now it's possible to show that all three definitions of nilpotency coincide. So, let A be a left Prelie algebra if L is nilpotent of nilpotency class n, then L has an upper central series of length n. And if L is nilpotent on nilpotency class n, then L has the lower central series of length n. So, and now I want to show the description of one generated nilpotent Prelie algebra. Not all, of course, but we start from nilpotent Prelie algebra of nilpotency class of 2. For this case, description is very simple. So I show this proof, but I want to show final result. So let A is vector space of dimension 2 over field F, and we define the multiplication by the following rule. Then A is Prelli algebra, and every nilpotent one-generated Prelli algebra of nilpotency class 2 is epimorphic image of this algebra. For class 3, we have the following. Consider the algebra A3. This is algebra. This is vector space of dimension 4. Addition is usual, and multiplication, we define the multiplication by the following rule. Then A3 is pre-Lie algebra. Moreover, this algebra is one-generated and nilpotent of nilpotency class 3. And this pre-Lie algebra play a following rule. Let L pre-Lie algebra generated by element A. If L is nilpotent of nilpotency class 3, then L is an epimorphic image of A3. For nilpotency of class 4, we have the following situation. Again, we consider the following algebra A4. This is vector space of dimension 8. And we define multiplication here by the following rule. Then A4 is pre-Lie algebra. This algebra is one-generated nilpotent of in nilpotency class of nilpotency class 4. And this algebra is free. So this follows from the following result. Let L be pre-Lie algebra generated by element A. If L is nilpotent of nilpotency class 4, then L is epimorphic image of A4. So A4 is free nilpotent one-generated algebra of nilpotency class 4. So I'm finished. Thank you very much.